Hello everyone, and in this video we're going to be looking at one of the more challenging exam questions in Math Studies exam history, or at least recent history anyway. And this particular question is question 16 of the 2010 SACE exam. So as we can see, we've got a few tangents, and it's essentially a calculus question. But it ends on a 5-mark question that involves probably a little bit more algebraic manipulation than what most people would be used to in mathematical studies. It sort of borderlines on the sort of algebra and the sort of problem-solving process that you would come across more frequently in specialist mathematics and math studies. But it's a good question, and I'm going to walk you through it today. So we start with a circle centered on 0, 0 with a radius of 1 unit. So obviously it has the equation x squared plus y squared equals 1, because it's centered on the origin. And you may be familiar, especially if you've done specialist mathematics, or you may remember from stage 1 mathematics, that this is a unit circle. We know that negative 1 is less than or equal to x less than or equal to 1 as a consequence of this. And we can see that originally in the diagram we just had that circle on the Cartesian plane. However, I've drawn a few other graphs because that's what it asks you to do later in the question. The very first thing we're asked to do for 2 marks is to find dy and dx for the circle. So we're given the equation of a circle, and it's quite obvious, especially from the math studies subject outline for the subject, that you should be able to get the result of negative x on y for a circle centered on the origin. This is explicitly stated. You've probably come across it before, no doubt, because it's quite a significant part of the differentiation subtopic. But if you need to actually find it for yourself and you can't remember that result, then it's just a matter of implicit differentiation. So we have x squared plus y squared equals 1. So therefore we apply the power rule, and we get 2x plus 2y times dy dx equals 0. Check out my implicit differentiation videos if you don't know how to do that. But essentially what I'm doing is I'm bringing down the power. The first part's really easy. It's just the power rule of x squared. And then the next part is just using 2y, which is essentially applying the power rule to that y squared term, but then we're multiplying by dy dx because we're essentially giving respect to x, because that's the variable that we generally differentiate with respect to. Hence we can rearrange to get dy dx on its own, so we end up with 2y dy dx equals negative 2x, because we bring that 2x to the other side. Dividing out, we get negative 2x on 2y, and we end up with the classic negative x divided by y result for dy dx. So that is the slope of the tangent to any point on that circle, which we know is c from before. It's given in the question. Okay, now on to the next part, so I'll just zoom in here. And we're asked to find the equation of the tangent to the circle at the point where x equals 0.3 and y is less than 0. So it's very important to read the question carefully here. So essentially what we're looking for is we're looking for what is the slope of, and I've added the line in already because I asked you to do that as the next question, the slope at this point here, somewhere where x equals 0.3 and y is less than 0. And as you can see, I've already worked out the value for that, but let's see how I did that. Okay. So first off, I substitute in x equals 0.3 into the equation. We have x squared plus y squared equals 1, because of course I need to know what the y value of that point is if I want to find the equation of the tangent to the circle at that point. So I get y squared is equal to 0.91 just by rearranging, bringing that to the other side. And when I take the square root of that, I get plus or minus this expression, but we know we need to go with the minus result because we know that y is less than 0. So we end up with y equals negative 0.95394. You can get that from the calculator. It's just the square root of that. Again, just really simple mathematics. We've just found the y coordinate for the circle. And what we do next is we use that y coordinate to get dy dx. Remember, it's negative x on y, but y is negative as well. So we're going to get a positive dy and dx. And when we considered the little diagram before, which I showed you, where I had that line, it's increasing slope, so it makes sense that we end up with that result. Because x is positive, y is negative. Okay, so then we use the tangent formula, so y take the y coordinate, but we have a double negative there because the y coordinate's negative, and we have subtract the y coordinate, so it ends up with positive. So we have y plus 0.95394. Now we have x take the x coordinate down there, and the x coordinate's positive, so it's x take 0.3. And we set that equal to dy and dx, because remember it's y take y coordinate, x take x coordinate equals the dy and dx for that particular point. Rearranging, we bring this up to the other side, and then we expand out. So as a consequence, we're obviously going to have 0.3145x take, and then we're going to multiply that by 0.3. And then, to get y on its own, we're going to move this to the other side. And when we do those two algebraic steps, which I've put into one here, because I didn't quite have enough space, so if I put that up higher, then maybe I might, but we end up with y equals 0.314x take 1.05. And that is the equation of the tangent to the circle at that point. We're asked to draw that on the following page, or on the page that was just there. So as you can see, it passes through roughly negative 1.05, which is the y-intercept as given by that linear equation. Then we have the point which we identified on the circle, and I've drawn a straight line through those 2 points there. So I've drawn the tangent to that point where x equals 0.3 and y is less than 0. It's important that they specify y is less than 0 because there's also another coordinate up here where there'd be decreasing slope. But we're only interested in where y is less than 0 because that's what the question says. And so the f of x equals x squared for our next function. And we're asked to draw x squared on there. Relatively simple. As you can see, I've got to go back again. But x squared is a parabola, and we can see, well, obviously negative 1 squared is going to be 1, 1 squared is going to be 1, so we can plot those 2 points. Negative 2 squared is going to be 4, and 2 squared is going to be 4, so we can plot that. We can try and draw a nice smooth curve through there. As you can see, I've partially done that, but I'm not as smooth as I used to be. Okay, so we've drawn our graphs on, and now we're getting to the fun stuff. This is where we're getting to quite a bit of algebraic manipulation, but it's going to be pretty fun in my opinion. So show that the equation of the tangent to the graph y equals f of x at the point where x equals k is given by that expression there. We consider the polynomial, because that's what it is. Y equals x squared is our f of x from before. And so what we have at the point where x equals k is the point k for the x coordinate and k squared for the y coordinate, because that's what x squared is when we evaluate it at k. So that's our point of contact. That's our point, and we have a tangent to that point. Okay? So remember, to find the equation of a tangent for anything, you need to have the point of contact, which is what we just found, and then the dy and dx at that point, and the rest is just an exercise in algebra. So what is dy and dx at that point? Well, as x equals k, the dy dx of x squared is obviously 2x using the power rule, but we substitute in k as x, and we get 2k as being the dy on dx, the slope of the tangent to that point of contact. So, the tangent hence has the equation of y take the y coordinates, so it's y take k squared, and then x take the x coordinates, so it's x take k, and that's equal to dy and dx, which we found to be 2k when x equals k. So now we bring that up to the other side and we expand out, so we get 2k times x, and then we got 2k times negative k, and what we end up with is take 2k squared there. So now we can rearrange, we can bring that negative k squared to the other side, it becomes plus k squared, and we end up with the form that they asked us to find, 2kx take k squared equals y. So that's not too bad in terms of algebraic manipulation, but the next 5-mark question is a little bit more challenging to follow on with, but I'll hopefully explain it in a way that makes a lot of sense. If you're doing specialist mathematics, it should make a bit more sense because you're probably used to being able to work with several variables, cancelling out variables, that sort of thing. So let me go over to the other side here, and let's have a look at the question. So I'll just center it up there. So tangent to the circle C at the point where x equals t, so x equals t, t is just some number, it's some parameter, anything, and y is less than 0, has an equation that we can see here. So y, it's giving us the equation of the tangent to any point on the circle C, and we're asked to find the values of t for which the tangent to the circle is also tangential to the graph of y equals f of x. So I've explained my logic here. So from the last question, in part C, we know that the tangent to the f of x polynomial, which was x squared, if you remember, is y equals 2kx take k squared. So the points, and there's probably more than one, because we've got a circle, but at the points where the tangent is both where tangent is both a tangent to a circle and f of x, we can use this expression found in C and make it equal to the expression that we're given in the question. So what we're essentially saying is, because we're looking at a point where the tangent to a circle is also tangential to the graph, these two things are the same. So if we look at their general form, we can say, well, 2k is going to be equal to the coefficient of x in this term. So 2k is going to be t on the square root of 1 take t squared. And we can also say that's a constant there, so negative k squared is going to be equal to negative 1 divided by 1 take t squared. And that's just a matter of identifying that those two are the same. And that's probably a tricky step, especially if you're not used to working with algebra, working with multiple variables like we are here. But you need to get that understanding of, well, if it's tangential to the circle, it'll be tangential to the graph at some particular point where t is a certain value and k is a certain value. And from there, we can start equating these two expressions in that way. So we've identified 2k as being equal to that, and negative k squared as being equal to that. And so we can start getting expressions for the variables t and k. Ultimately, what we want to find is we want to find t at a certain point. So we're going to have to work out what k is first, because we can't quite get rid of it at the moment. So by equating, as I just said, t on the square root of 1 take t squared is equal to 2k, and likewise negative 1 on the square root of 1 take t squared is equal to negative k squared. Doing some rearranging, I bring the 2k down and I bring that one up. So you can probably see here there's a unique term. We've got 1 take t squared, the square root of that, appears in both of these expressions. So because that's a square root and it's pretty nasty to work with, we can actually cancel it out by getting two separate expressions for that. And this is where sort of the spec algebra problem solving approach comes in. And if you're doing spec, this should make a lot of sense. If not, then just bear with me. Hopefully it will make sense when you've seen the full solution. If not, leave me a comment below in this video. So we've got t on 2k here, because we brought that up to the other side. And then we've got negative 1 divided by k squared when we bring that down there. And sorry, it's negative k squared. So negatives cancel. As you can see here, we got 1 on k squared is equal to that. And hence, what we end up with is this equality here, where we have the square root of 1 take t squared equal to those two things. So from that, we can get rid of the middleman. We no longer need that. We can let 1 on k squared equal t on 2k. From there, we can bring the k squared up to the left-hand side, and we can bring the 2k up to the right-hand side, so we get k squared t equals 2k. And now what we want to do is we might want to bring that 2k to the other side, so we've got negative 2k. And what we can actually do is we can factorize to find a value of k here. So, once we do that, we see that k is a common factor between the two terms on the side, so we can isolate that. And so what we end up with is k multiplied by kt take 2 equals 0 there. Now we know that k is not going to equal 0, and we can refer to our graph for an explanation on that. Because if k is equal to 0, and we remember what k is, and we're looking somewhere in the circle, and definitely not a tangent to the circle, maybe a tangent to f of x, but not a tangent to the circle, because x equals 0 doesn't make sense. Because remember, x equals k from before. Same sort of logic here. So we discard that solution. And the reason I came up with that solution, we've probably zoomed in a bit too far here, but that doesn't matter, is because we got k here outside the bracket, and we got 0 on the other side. So either what's in the bracket equals 0, or the other thing in the bracket equals 0. Because you may remember, based on multiplication, anything times 0 is 0. Well, that's the logic we're using here. So either that's 0 or that's 0. So that's definitely not going to be 0, otherwise, yeah, that doesn't really make sense. So we are stuck with the other one. K equals 2 on t is a result of this, because we know that this must equal 0 now, because that can't equal 0. So kt, take 2 equals 0, we bring the 2 to the other side, and then we divide by the t. So what we end up with is k equals 2 on t. And it sounds like my laptop fan is really enjoying this algebra as well. Anyway, so the next process is to remember from before that we had an expression for tk, and we can use this expression to find t, because we now know we now know t infinity and vice versa. So t divided by a square root of 1 take t squared is equal to 2k. We know that from before when we did our little equating. And that's now equal to 4 and t. So now, no more k. We don't need to worry about k anymore. And now we can just solve it. Simple to do. What we do is we just, bring that to the other side. We need to square both sides, so that goes up to there. That becomes t squared, and that becomes 4 lots of square root 1 take t squared. We square both sides, so we're going to get t to the 4 here. And that's where things start to get a little bit scary, but don't worry, you've got technology to help you in the exam. They don't expect you to be able to solve a quartic, not in studies and not in spec either. So don't waste your time, it's only 5 marks. And then from there, what we do is we expand out just using FOIL. So we brought that to the other side. Again, we squared both sides, so that's 4. That 4 becomes 16, and there's no longer a square root there. We expand. And as you can see, what I've just done here is I've multiplied through by -1. So I brought that to the other side, and I've noticed that's negative t to the 4. And then we have plus 16, and then we have take 16t squared. But I'm like, well, we have two things that are negative. May as well multiply through by -1. Make it nice and easy. Don't have all these negatives. Be positive. Be happy. It's almost over. This is the last question on the exam. And from there we have a quartic we can work with. We've got that equaling 0. So now what we do is we hand it over to our calculator. I'm going to show you a little bit of a demo how to do it on the TI. In fact, actually, no, I probably won't show you how to do it on the TI. Depends, do I have the simulator installed? Let's just have a look here, TI 84. If I do, then I'll show you. Yes, I do. It's your lucky day. And Java doesn't want to run. Okay. But anyway, just take my word for this. The best way to solve it, I'll talk you through the menus, even though I can't show it up on the screen. But the best way to do it is to press the apps button. It's a purple little button. If you've seen my other videos, you should know how to do this. But go down to the option under apps that says PLYSMLT2. Then press enter. Press enter again. You should get Polyroot Finder. You need to press enter on that. Change the order by using the arrow keys and go to the 4. And then you should just be able to press next. Now insert where it says A to the 4, this is the instructions for TI-84, so hopefully you're following along. If you have a Casio, I'm sorry. But what you can do is you can go to your y equals, type in the function, and then just evaluate when that function equals 0. That's another alternative, but for the TI there's a native app and I know how to do that. Where it says A to the 4, put in the coefficient. And the coefficient there is 1 because we have 1t to the 4. Then we have nothing to the 3, so put 0. Then we have positive 16t squared, so next to A2 put in 16. Then we have A1, which is 0 because there's no t term there. And then A0 is the constant, so we have negative 16, so make sure you put the negative in. And it spits out a few values. A couple of them are complex numbers. If you have that turned on, you'll be able to see them. It's where we have a number multiplied by I. Doesn't really matter. If you're doing spec, you'll know what's going on, but it doesn't really matter if you're not. And then you can see the last two solutions are real. And we have plus or minus 0.97 and I'm just going to round it to f here, so 0.972. And that's where we have t tangential to the circle, and also the polynomial f of x. So hopefully this video made a bit of sense. Let me know if you have any questions. Again, that last question at 5 Mark 1 is one of the more challenging ones I've seen in a math studies exam before, but it's a good one. It's a fun one. It's a good calculus question. I like it. So yeah, thanks for watching. See you.